Okay, in the first video on the Laurent series, we mentioned that one of its attributes is that it can be used to classify singularities. Okay, in this video, we're going to see how that happens. So we're going to look at the different types of singularities. Now, the first type is called poles. Now, if the principal part, so remember the principal part of the Laurent series is the part involving negative powers. So if that one has a finite number of terms, so like this one, and if the last term is of the power n, then the singularity z0 is called a pole of order n. So if you like, so these poles are zeros of the denominator. So you can see this one is a zero of multiplicity n, so we call it a pole of order n. So if the order is 1, we call this a simple root. So parallel to the idea of a simple, so we call this a simple pole, parallel to the idea of a simple zero, a simple root. If the pole is of order 2, we call it a double pole. If the pole is of order infinity, so that means we've got an infinite number of terms here, then the pole is called an essential singularity. Okay, then the next one is what we call the removable singularity. So in this case, if the function is not defined at z0, but the limit as z goes to z0 of f exists, then z0 is called a removable singularity. So typically, if z0 is a removable singularity, then the principal part of the Laurent series is going to be 0. So there are not going to be any negative terms in the Laurent series of f, which is centered at z0. Okay, so let's have a look at a few examples to see how this works. So all these functions here given are singular at z0. So what we're going to do is we're going to find the Laurent series at 0. Then we're going to use it to classify them as, well, whether it's simple poles, removable singularities, etc. So since we are at 0, we are typically going to use the Maclaurin series wherever it may be applicable. So the first one is sine z over z. So what we're going to do is we're going to write this. So we're just going to expand sine z in powers of z. So this is going to be z minus z cubed over 3 factorial z to the power 5, etc. Then if we remove the brackets, it's going to be 1 minus z squared over 6 plus z to the power 4 over 120, etc. At which point we notice that this just has got no negative powers, because so this implies that z equals to naught. So z equals to 0 is a removable singularity. So we are going to be familiar with the fact that the limit as z goes to 0 of this is 1, even though it is not defined. So that is the reason why z equals to 0 is a removable singularity. Okay, so in the second question, we've got 1 over z to the power 5, power 3 minus z to the power 5. So 1 over z cubed minus z to the power 5. First thing I want to do is factorize here. So we're going to have z cubed 1 minus z squared. And then what we're going to do is we are going to write this as 1 over z cubed and 1 over 1 minus z squared. And then this second one here, we can expand in powers of z using the geometric series result. It's going to be 1 over z cubed times 1 minus, it's actually going to be plus z squared plus z to the power 4, etc. And then if we multiply through here, it's going to be 1 over z cubed plus 1 over z plus z, etc. Now we see that the biggest, just need to mention the radius or the region in which this series is going to be convergent. So this series is going to be convergent so long as mod z is greater than 0, because of this term here. But this one here is going to be convergent inside the unit disk. So that's going to be the region of convergence. So it's actually going to look something like this. So it's a disk of radius 1, but the center is excluded. So this is a so-called punctured disk. So that sequence or series is going to be convergent in this punctured disk here. But to answer our question, in this case, the highest power, negative power, is 3. So we're going to say z equals to 0 is a pole of order 3. Order 3. So that is the second question there. In part C, we have f of z equals z squared e to the 1 over z. So part C, f of z equals to z squared e to the 1 over z. So if we expand the e in so it's going to be, so the Maclaurin of e to the u is 1 plus u, which is 1 over z in this case, plus 1 over, plus u squared over 2 factorial, so there's going to be 2z squared, etc. If we multiply through by the z squared, so it's going to be z squared plus z plus 1 over 2. Then the next one is going to be 1 over 6z. And then, so that's 3 factorial. And then 4 factorial is 24. So what we notice here is that the principal part of this starts here, and it's going to be an infinite number of negative powers. So this thing is telling us that z equals to 0 is going to be an essential singularity or a pole of infinite order. So this is an essential singularity. And of course the the region in which this thing is going to be convergent is going to be everything bigger than 0, magnitude of z bigger, not less than 0, bigger than 0. Okay, let's see. In D, we have f of z equal 1 over 1 minus e to the z. So f of z equal 1 over 1 minus e to the z. So as you can see, well, when z equals to 0, it's going to be 1 over 0. What we're going to do here, again, we're going to use the Laurent series of E. So in the denominator, we're going to have 1 minus 1 plus z squared over 2 factorial, z cubed over 3 factorial, etc. Then when we remove the brackets, this thing is going to be the negative of z plus z squared over 2, z cubed over 6, etc. However, z is now common, so we can factor out z. It's going to be 1 plus z over 2, z squared over 6, etc. Now we notice that 0 is a simple root, or a simple, it's a simple root of the denominator, because this is to the power of 1. So whenever that is the case, it means if we expand this in powers of z, then there is always going to be the highest negative power is going to be 1. So this is implying that z equals to 0 is a simple pole. Okay, at this point we are going to give you an opportunity to have a go at the 5 remaining examples here. If you just want to pause the video and then work through these ones, then when you continue the video, you can compare with our solutions. Okay, we're going to scroll down to our solutions for E, F, G, and H now. I would like to thank you for visiting our channel and watching our videos. We hope that they are useful to you. We do implore you to subscribe to our channel to support the work we do, so that we can produce more videos. If you've got any questions, we would like to hear them. Just post them in the comment section. All right, so for this one, we are going to expand cosine in its Taylor series about the origin, which is this, and so the ones cancel out. So in the numerator, there's a common factor of z to the power 4. So when we simplify, then the series looks like this, of which you can see that there is no negative powers, so z equals to 0 is a removable singularity. This one, we first factor out 2z, and then we write this in the form 1 over 1 minus something. That something becomes z squared, negative z squared over 2. So then in terms of the geometric result, that gives us this. This sequence series is going to be convergent as long as the magnitude of this is less than 1. Then multiplying through by 1 over z, we see that the highest power of z that's negative is 1, so it's a simple pole. Then in terms of the convergence of this series, it's going to be in this punctured disk here of radius √2. For G, expanding this again in Taylor series about 0 gives us this, and then multiplying through by z squared, then we end up, we still have a 1 over z here. So that tells us this thing is going to be a simple pole. Here again, expanding this in terms of cosine, the ones cancel out, and then we can see that 0 is a double root of the denominator. So when that happens, it means it's going to be a double pole of f of z. All right, thank you.